break if is over and we can start the next session.
Okay. So the last talk in this session 10 is keynote talk. Exo-planets, life for lessons and lessons for life. Life for lessons and lessons for life. Presented by the Chandra Nautiyal. Are you ready?
Yeah, I'm ready.
Okay. Then please start your presentation.
Good morning, everybody. And as we know, the true astronomers work at night. And as I can see that for many of you, it's either very early morning or maybe late night. And I'm really thankful that all of you have bothered to be here and to come and listen to this lecture. I'll be talking about something which is literally exotic. Well, astronomy, all the objects are exotic. And we will be talking about, just a second. I think, is my voice clear?
Yes, it's clear.
Yeah.
Let's try to use a microphone. Am I audible now?
Yet we can see very well, but would you use the presentation file?
No, I mean, is my voice audible? Are you able to hear me?
Your voice is fine. We can hear you.
Okay, fine. Okay, so I will be talking about exoplanets and the reason why we are interested in the exoplanets. And I would like to start with my screen sharing.
Yes, please.
Yeah, is it all right now? Can you see the
now
screen?
it's the editorial mode. So the please start the presentation mode.
Okay. Is it okay now?
We can see, yeah.
Fine, fine. I'll be talking about exoplanets, and let's know this. The main question which has been facing the humanity for many years is there life anywhere else in the universe? And we are not the only people who think about it. The famous nuclear physicist Enrico Fermi once said, "Why haven't we already encountered extraterrestrial intelligence if it's common throughout the universe?" Another one said, "If they were there, we would have seen." But Carl Sagan and William Stein Norman said, such advanced forms would have self-destroyed, either through nuclear or biological or warfare or some such thing. So is there really life anywhere else in the universe? Brown said, our sun is one of 100 billion or so stars in our galaxy. Our galaxy is one of billions of galaxies populating this universe. It would be in the height of presumption to think that we are the only living things in that enormous immensity. And the famous philosopher Socrates said 500 years before Christ that humanity must rise above the earth to the top of the atmosphere and beyond, for only then we'll be fully understanding the world in which we live. These are all really prophetic statements. And now that man is capable of flying into space and able to look at Earth and other places, it has become possible for men or people to think about whether there is life elsewhere. Humankind has always nurtured a hope, howsoever faint, howsoever feeble, that one day they would find life beyond Earth. The search for exoplanets is strongly fueled by this wish. The challenge of finding another planet far away, small, faint, but perhaps teeming with life is much more exciting than just finding a planetary body, howsoever big or howsoever small. A planet that is not within our solar system is an extrasolar planet, or in short, we call it exoplanet. And that is the subject of my lecture. In principle, a planet outside the solar system can have life, even intelligent life. Just that so far we haven't come across any such planet or any such form of life. Actually, life requires there should be seed for life, as people say, panspermia, which means life was there around some other star, and inside a planetary body, inside some part of a comet, inside the part of some meteorite or asteroid, that thing landed on Earth, and life started on Earth 4.5 billion years ago. Or if it were there at some other place, then how then it started there? Which means at some stage, there was a transformation from inorganic material to the organic. Then its survival, then it was nurtured, grew, and then it went on further to evolve into intelligent being. I must also clarify that the visuals that I am using in today's lecture, they're not obviously taken by me. Most of them are by astronomers or by different laboratories. They have been taken from NASA, European Space Agency, or European Southern Observatory, JPL, Caltech, and numerous sources on net, and I have attributed in the slide. Generally, all the artworks, I must caution you, they are not real. Many of these are artworks because exoplanets have not been imaged that much. So these are artists' imagination combined with scientists' input. So please don't take those paintings literally. The first report of discovery of extrasolar planet, or simply exoplanets, was around pulsar. Pulsar, as you know, are sending electromagnetic signals to us periodically. They could be neutron stars, and by neutron stars, we mean stars which are composed of neutrons without electrons or protons. As you know that the size of the atom is very huge, but the nucleus is in the center in the classical picture, and it's a very small part of the whole atom. If you remove the electrons, remove the protons, and only nuclei are left, or only neutrons are then left, then it becomes a very small body, but with more or less half the mass. And at the same time, that makes it extremely dense, and therefore the gravity is also very strong. There are some nebula inside which people suspect that there are pulsars, like trap pulsar you see here. In the center of it, there is a pulsar. Now, pulsar PSR 125712 was discovered in 1992 by Alexander Volskazin and Il Frail. And later there was observation of another 51 TSCP, first exoplanet discovered around a sunlight star. That was in 1995. In other words, before 90s, no exoplanet had been discovered. But let us think about it once again. Now that Pluto is out of the planet's fraternity, Pluto is actually another planet which is not part of the solar system. So technically, Pluto is also now an exoplanet. The Nobel Prize in 2019 and to Michael Mayer and Didier Queloz for the work in this field. In this lecture, since many of us are teachers, so I would also like to tell about some learning opportunities. For example, this slide gives some idea how to tell the students about pulsar, Pluto. We can also discuss with them the criteria for being a planet. We can talk to them about the orbital planes and so on. One important activity that could be done in the class is based analysis of the available data to learn about extrasolar planets. There is a paper in 2011 in physics education by Samuel J. George from the University of Calgary, and he published a paper where he has discussed in detail how, by looking at the data available on net, students can be told to analyze that data. They would look at the luminosity coming from the star, and then an exoplanet passes in front of it. There is a dip in the light or radiation coming from that star, and we know that something is obstructing it. And this happens periodically because if it's a planet, it will be revolving around that star very regularly. But how do we detect the exoplanets? This was one way. There could be direct imaging also. These days we have satellites, we have Hubble telescope, we have other such stations who can directly photograph. And the advantage of the space telescopes is big. There is no turbulence of the atmosphere to interfere with clear images. Therefore, these satellite-based cameras, PCDs, they allow us to image the planets without disturbance from the turbulence of the atmosphere, which sometimes make the pictures very bad. In the star's brightness, we just talked about, I'll discuss it in detail a little more. There is micro-lensing, that is because of the gravity of the body, the radiation coming from behind it is bent, and that gives us an idea of the mass of that object. There is a radial velocity method because if it's a planet, it's revolving around a star, which effectively means this is coming close to us and then it's going back. Now, this is a real situation if we are in the same line of plane as the planet, but if the planet is almost at 90 degrees to us, we will not be able to see very clearly this distance. Then there is a method based on relativity. So why we are interested in these exoplanets? We also have to understand the concept of habitability. There are some planets which are at the right distance from the sun. Now, let me also clarify one thing. When we say habitable planet, we mean where life such as ours can survive. If there is some form of life which is very different from us, for example, if we require 20, 30, 10, 50 degree kind of degree Celsius of temperature to live, this kind of life is suitable for Earth. In a different circumstances, we do not know whether life of a different type would have evolved and nurtured. There are some planets, exoplanets like Qatar 186F, which have been discovered, and it seems that they are at the right distance from the star so that the temperature is good enough. And if they were water, it could survive there in the liquid state, and the brightness of the star is just right. The rotation period of the planet is okay, and there are not too strong winds. So in other words, what we can say is that the planet is habitable if this is at the right distance from its star. The temperature of the star is such that the temperature on the planet is also comfortable and good enough to permit life. So how do we get to learn about these exoplanets? They are very far, many light years away. And directly imaging them is actually more difficult than it appears. We might think that in the age of chargeable devices or CCDs, it should be easy to photograph them. But then look at the contrast between the temperature of the star and temperature of the planet. Here you see a planet around GHOU UP. It's from Radial Observatory in Chile, European Southern Observatory. The photograph was taken 16 years ago. You can see where you see this small b written, that's planet, and the body, the white body at the left is the star. Now the temperature difference is so much that the luminosity of these two objects is very different. So photographing these two very, very contrasting objects, huge challenge. Now these days people can use coronagraph, which can cover the star, and you can photograph the planet without interference from the light from the star. The distance between this GHOU star and its planet is around 20 times that of Jupiter from the sun, which makes it around 100 astronomical units. Originally, in the year 2005, when it was found, people thought that it's a possible candidate, but in 2020, it has been confirmed to be a planet. Now, this slide gives you an idea. You can use this slide to discuss with students about coronagraph about space telescopes, about atmospheric turbulence, and scattering of light. There is another NASA's Hubble telescope. Being outside of the atmosphere, it makes it possible to take clean photographs. There are some other agencies involved in photographing these exoplanets, like European Southern Observatory ESO, which is in Chile. In Hawaii, we have the Keck Observatory. There are some other laboratories, observatories, and telescopes which are active, and they have discovered some more than 4,000. I think the current number stands at somewhere almost close to 5,000 exoplanets that have been discovered. And there is a larger number which is still in the hold position, which means people are not sure, people suspect that they are exoplanets. Now, out of these about 5,000 exoplanets, not all are habitable zones, which means it's not necessary that the life or the conditions good for life may exist there. There may not be life at all. And even where it's an habitable zone, it does not mean that life originated there. It does not mean even if life originated, the life survived there. And this is not necessary that the life evolved to a stage where it turned into an intelligent civilization and it is capable of sending radio signals to us. For example, you must be knowing that when the pulsars were discovered and the electromagnetic signals were detected, people first thought these are signals from some other galaxy or maybe some far away civilization. But then this turned out that it was not the case. This was not from an intelligent civilization. They were coming from a natural object, and their periodicity and all were checked. And as you know, the Fritz got Nobel Prize after his team, including Jocelyn L. They observed. In 2005, this was discovered, and this is almost double the size of Jupiter. And the mass is much more, and its temperature is also very high. So it doesn't look like there would be life. This was a direct imaging thing. Now, dipping up the brightness during transit is another way to detect. This is again a photograph from the literature. You can see the star here. And in front of that, you see that there are planets which are moving. I mean, it's the same planet shown in different positions. So whenever a planet blocks light coming from the star, there is a dip or decrease in the brightness of the star. And in the very initial stage, when it's in the corner, this is less, but gradually this dip starts becoming stronger. But even then, you must understand that this dip is not really very much. Given that the size of the planet and the size of stars are very different, this dip could be as low as 1%, although in some favorable cases where the orbiting planet is huge and it's very close to the star, the dip could be as well as 2%. But we should also know that if the planet, we are looking at this planet and the star, not in the same plane. For example, in blue color, I have shown you some imaginary planets. This is moving like this. In that case, there is not going to be any dipping, even though the star may be having a planet. Radial velocity method or the Doppler method is another method. What we mean by radial velocity method is when you know from the Doppler sound observation that when an object is moving away from us, the wavelength gets stretched. And when it's moving close to us, the wavelength is compressed. There is a change in the frequency or the wavelength of that object which is coming close to us or which is moving away from us. And if this is a planet, and if this is in the same plane as ours, we are looking at on the edge of it, it's an edge view, then we would see that the radiation coming from that star, from that planet, is actually gradually and systematically decreasing and increasing in the wavelength. NASA's Kepler spacecraft have actually used this technique to detect most of the planets which have been found so far, and almost 3,000 planets, potential planets, have been discovered since March 2009 when the Kepler was launched. It's a very important technique, and now there is capability with astronomers to detect these motions even if they are very slow. example, 1 meter per second. Now, planets like Jupiter, which are huge, they can make this to be something like 12.5 meters per second. And since our detection limit is 1 meter per second, it can be easily detected. One can see the bubble because what actually happens is if you look at it from the top, look at the figure at the left top. If you are looking at it from the top, you would see that actually the star is moving in a small circle. And this makes us understand that there would be a change in the distance. There will be it will be moving away from us, or it will be moving towards us, and there could be a change in the frequency, and we can detect that. Another thing is pulsar. Pulsar in the same way, if pulsar is sending towards us electromagnetic signals, then what happens is if a planet comes on in the way, in that case, that the signal is interrupted, and we are able to realize that there may be some object between us and the pulsar. And if this happens periodically, that gives us a clue that pulsar is there, but there is some planet around it, or there is some other planet. In fact, even if there is a rogue planet, which we do not know to which star it belongs, if any rogue planet is also moving close by and it blocks the radiation, we would know of this planet. Microlensing is a gravitational effect. I know that the radiation can be affected. There is a nearby gravitational field which is very massive. What happens is if there is a massive planet moving around a star, the nearby object's gravitational field bends and magnifies the light from the star. This is almost like a lens which focuses the light and enhances the effect. This produces a brightening and fading of the faraway star's light over time, and we are able to see that this gravitational lensing or micro lensing is there. Therefore, there has to be a massive object there. There are a number of exoplanets which have been found by people. I will just show the photographs. These are not photographs, actually. These are artist imagination, because in every case, it's not possible to image. And the images, even if taken, are not very clean. Chandra X-ray Observatory, it's named after the famous astronomer or astrophysicist S. Chandrasekhar of Indian origin, who got Nobel Prize for his work in astrophysics. This is with the Chandra X-ray Observatory and the European Space Agency's Newton's X-ray telescope. HD 189733, it's a bluish marble, and it seems that when there is the strong velocity of the winds there, because it's moving very fast, there is silica which gets out of the ground, and there is rain which is made of silica and not water or any methane or ammonia. There is another one, WASP 76P. This is tidally locked to the star, which means on one side of it, there is a day always, on the other side, there is night always, and the strong winds here carry iron vapors across the globe, and so when it rains, this is not again water or methane or ammonia, this is iron rain. Kepler can be, it was detected using relativistic method. The star brightens up and it's struck by an orbiting planet. These photons pile up in the energy, and the light is focused in the direction of the star's motion due to relativistic effects. So this Kepler-10b is another exoplanet which has been concluded to be existing. These 1132b is very interesting. This is 2 to 3 times bigger, massive, actually, as massive as Earth, and the size is like Earth, so this is more dense. And people say that this is a place where there could be alien life, but there is no evidence so far which can prove that. But people think that its distance at 20 light years from Earth, orbital period of 30 days, this perhaps can have suitable conditions there, so it's maybe habitable. But being habitable does not mean that there is life there. Upsilon Andromeda, this is an exoplanet, and it has a very high varying temperature, and the temperature on the night side, this again is locked. Therefore, on the night side, the temperature is very low. on the star-facing side, the temperature is very high. Similarly, there are some other planets which have been detected using these different methods, and some are tidally locked, some are not tidally locked. Similarly, this 55 entry E, this again has a very high temperature, and people think that its density suggests and its compactness suggests that it may be made of carbon, and some people suggested that this may be made of a diamond. If this is really true, then this must be the most expensive piece of rock in this universe, if this is made really of carbon, of a diamond. A diamond, as you know, is a result of carbon at a very high temperature or very high. But why are we interested in exoplanets? We are interested in exoplanets because we are also looking for life. We know that life on Earth is possible because we are at a distance from Sun where the temperature on Earth is a few degrees Celsius, maybe 45 or 50 degrees Celsius. These are conditions in which life can survive, or life as we know it. We have very cold places on Earth. We have very warm places on Earth. But then there are places on Earth which appear to be uninhabitable, such as the depth of Antarctica. People would never imagine that there could be life under the ice sheets in Antarctica, but people have observed now that there are lakes there like Violence Lake, Ellsworth Lake, or Vostok Lake, and people have gone to the depths of as much as 3.7 kilometers, and they have found bacteria there. These bacteria were such that they could even be cultured in the laboratory, which means life can be there under the conditions where we think life to be impossible. Makes exoplanets study even more important because we are always looking at exoplanets and we take interest in only those exoplanets which are at a proper distance from the star, so that they are in the habitable zone, so that water could exist there, at least in liquid form, not all the three form. We expect that there would be conditions like wind conditions and other things so that life would be possible. But now there are two things for the life to be there. One is there should be the right elements there, elements which allow life to be built up. For example, on Earth, hydrogen, carbon, nitrogen, oxygen, and phosphorus, and copper, and zinc, and all those elements are available. Now, these elements could combine and form life, and carbon is very essential because this is tetravalent, and it can form gas, it can form liquids, and it can be in different forms. Similarly, the temperature is such that there is water, which is a great facilitator for chemical reactions. We are interested in exoplanets also to understand if life is possible there, but only problem is that we always look for life of the same types as we have on Earth. If we take this simplistic view that the essential raw material for life and the required reactions to convert inorganic into organic should be there. In case of Earth, it was shown around 1950 by Miller at University of Chicago that inorganic materials like methane, ammonia, carbon dioxide, and water, these things by electric arc or by producing artificial lightning, one could convert them into amino acids, and amino acids, as you know, are the building blocks of life. Second requirement is a stable landmass. Of course, Carl Sagan said, what is wrong with clouds? In fact, there is a famous science fiction black cloud, which some of you may have read, where life is there, but inside a cloud. But still, we believe that for life to prosper, for the life to evolve, perhaps a stable landmass would be needed. There has to be protection from ultraviolet radiation. This radiation could be, this protection from radiation could be in the form of ozone layer, could be in the form of layer of water, or it could be in the form of some change in the physiology of the living beings where they are protected through their skin from the ultraviolet. We don't know, but people believe that on Earth, life originated perhaps in water, or in at least the puddles of water, where they could protect themselves from the bacteria to protect themselves from ultraviolet radiation. Otherwise, they would have been killed. We feel that oxygen is necessary for our survival, but the plants think otherwise. The plants believe that carbon dioxide is essential for survival. Need for different forms of life could be different, and perhaps our view is very, very limited. So, what could one expect on a planet as evidence of life? This is another question. What is it that we call life? When we define life, we usually mean life like people who eat, people who live, people who multiply, people who react to situations or to when something excites, but there are stimulants, things that can move, things that can reproduce, or which have genetic material. But now we look at many other things which we consider not live. They don't have all these properties. Or some of them have these properties, but they're not living. For example, fire consumes material, produces energy, but is not living. Mules are living animals, but they cannot reproduce. Robots, such as now on the surface of Mars, the buggies or the rovers, which are on the surface of Mars now or Moon, these rovers are moving. They detect an impediment on the way, any hurdle on the way. They can change their direction, but that doesn't make them living. Artificial intelligence, which can analyze to some extent, is not living. So first thing is, we are not sure what is the definition of life, and therefore we do not know what to look for on exoplanets. But some things people are right now agreed upon is that if there is life of the type we have on Earth, there would be methane on those exoplanets. These gases can be detected even spectroscopically from Earth itself. And GSFC Goddard Space Flight Center have achieved some successes from their monarchy observatory. They have been able to detect methane on Mars, in the Martian atmosphere. But the question is whether this methane is of organic origin or inorganic origin. Similarly, there are some other laboratories which were detected, but it's not very easy to find from Earth whether the methane is of organic origin or inorganic origin. If you could somehow get a sample of that methane, then perhaps you could subject them to isotopic analysis and try to see whether the ratio of carbon-13 to carbon-12 resembles the living things or inorganic material. We also expect that for the kind of life we have, there should be oxygen available on those planets or exoplanets. There should be light for plants because they have to photosynthesize. But then people have found, this was in 2013, in 2010 in Nature, this paper was published, about millimeter-sized objects were found. They were multicellular life forms in the depth of the Mediterranean Sea, where there is no light, there is no oxygen. These were smaller than 1 millimeter. They were called Loricifera and they were metazoans, and they have been found from some other places also. Earlier, people thought that life cannot exist in those conditions. But now we have found, which means when we are expecting life on other planets, we may be wrong. Our expectations may not be always right. There are other kinds of life forms which you find in the sea. There are some things which at a particular angle, they just vanish. There are things which can survive under very, very cold circumstances. They start producing some chemical. It changes their properties. They can go into hibernation, and they, once the temperature is favorable, the chemical production stops, and they again come back to life out of their hibernation. So many such things have been happening. People have been really now made to think whether life is of the same form as we have here on Earth, and there could be other forms. For example, bacteria, eukaryotes, and viruses, or extremophiles. When we talk of extremophiles, in California, there is Mono Lake, where under the extremely salty conditions, bacteria could evolve themselves to be able to survive in highly salty conditions. So I think we require a change in thinking. We have been given some hope. For example, many years ago, when a meteorite was picked up from Allen Hills by the Antarctica scientists, by the workers, in a rock which was used to be from moon. Something like a bacteria, which you see in this photograph here at the bottom, something like a bacteria was seen, but later claim was discarded. And as somebody said, that extraordinary claims require extraordinary evidence. This is detected because the size of the bacteria was very small. Again, there is no reason why on other planets or on exoplanets, the form of life should be of the same size as on Earth. But most likely this was contamination. A contamination when the material was being plated or was being coated with the gold and palladium for the study in the scanning electron microscope, in an electron microscope. Similarly, some other contaminations were also found, which said that perhaps this is not a bacteria, but then the hope is always there, because life forms can be in very strange forms as we see them on Earth also. These are the different forms of life which have been found in billion-year-old or around that rocks, and these are the life forms. So perhaps when we look for life on exoplanets, we look for signs of life on other planets, we should be very cautious. Life on Earth has become possible because it was protected from the ultraviolet rays, and therefore people believe that life originated in the ocean depths. Earth was massive, it could hold the atmosphere, which many of the exoplanets don't have. Those who are very close to their star have all of its atmosphere, if it were there, all of it shattered away because of the radiation from the sun. Earth has a magnetic field which prevents the high energy cosmic rays from directly coming to the Earth. They are diverted towards the poles. We have an atmosphere which prevents us from the asteroids which come from the space. We have atmosphere which keeps the water on Earth in the liquid form, which is so essential for us. We have atmosphere which formed ozone layer, which protects us from the ultraviolet rays. And the distance from our star sun is just right. The temperature here is such that we can survive. There are liquids here which facilitate chemical reactions. The Earth rotates not too fast, not too slow, and therefore, if you make any structures on Earth, they can survive. At one astronomical distance, that is the distance from the sun, the temperatures are tolerable. We have water which allows rain. It also was important for one more reason. Whatever carbon dioxide we had initially in the atmosphere, just like Venus, it all had been washed down to Earth and deposited in the ocean in the form of carbonate. Did not have water. If there was no hydrological cycle on Earth, we would have been having a lot of carbon dioxide in the atmosphere, and we wouldn't be surviving. All these things made it possible, perhaps, those small bacteria to come up. They survived, and there was explosion of life. Another question comes that, should we expect the life only in the form in which we see it here on Earth? Why should oxygen or water be essential for others, some different forms of life? Why should they depend only upon radio or electromagnetic signals to communicate with us? How will they communicate with us? Perhaps methods by sending to us their pictures, which are in the binary system, which are in the electromagnetic signal. Signal means 1, no signal means 0. So the 0 and 1 binary system can help them to communicate with us. But then again, maybe they're too intelligent. Maybe they're too advanced, and they are using some method which we do not know. Or maybe they just don't have interest in us. So in today's age, we have a lesson for life that we are looking at exoplanets. We are trying to look for life on some satellites like a moon, on planets like Mars, but also in exoplanets which are many light years away from us. This is because today we also realize that life today on Earth is under. This is due to a very, very small 80 or 100 nanometer virus. So we have to know what kind of conditions are there in other places, and we don't know at what stage human beings may have to escape for light other planets or exoplanets. This is also an opportunity for the teachers in the classroom to talk to students and tell them what has made life possible on Earth when they tell them about the exoplanet. In what way we have been fortunate to be here, and the life can survive here, hopefully for billions of years, maybe about 4.5 billion years, because after that time, perhaps sun will change its properties. It would have lost a lot of mass because of radiation from it, because the conversion of its mass into energy continuously for billions of years. It will be gravitationally weaker. Earth will move away from us. That should cause the temperature to fall down, but at the same time, perhaps sun will also expand and envelop the Earth within us. We do not know. There are many such possibilities, but again, the search for exoplanet should continue. It should also give us an opportunity in the classroom to tell students about how a star forms. What is the source of its energy, like nuclear fusion? What is the relationship between wavelength, frequency, and velocity? What we mean by spectrum and spectroscopy? How Doppler shift works, and it also helps us in detecting the exoplanets. Then we can have data for many transiting system on the net. For example, for extrasolar planets encyclopedia, this http://exoplanet.GHOU. This is a very good site where you find a lot of data. The teachers who help their students analyze this data, as has been done by Samuel in one of the papers which I mentioned in the beginning in 2011. And the students can look at these extrasolar planets and try to learn what they're about. The search for exoplanets continue, because it's whether we find them or not, it's a win-win situation. If we find the extraterrestrial life on those planets, it's mission successful. If we don't find, we prove our uniqueness. So we can take pride in either of the situation. So stay safe, stay healthy during the difficult times. There is a saying in Sanskrit in our country which says, Sarve bhavantu sukhinah, Sarve santu niramayaha, Sarve bhadrani pashyantu, ma kasyat bhaved. And literally it means they all be happy, they all be free from diseases, they all be good, they no one suffer grief, less peace. Thank you so much for very patient listening.
Okay, thank you for the very impressive and comprehensive review of the exoplanet. So now we have not yet any comment or questions in Q&A, but I have one comment in chat field. It has been a great variant address, opening up the new horizons in the dimensions of thought to ponder upon. Rightly said, these are great insights. So, is there any other comments or questions? So actually, in my university class, it is general education. So I have the one-term lecture on the whole astronomy from the moon to the cosmic background radiation and Big Bang. And the last lesson, I give a lecture on the extraterrestrial life, including the Drake formulation. And I request to submit a report on the how to find the exoplanet. So depending on their own subject in the university. But unfortunately, the most students think little. So it is I am wondering what should I do to thinking about much on about that. So do you have any idea, Chandra?
Can you please, in short, repeat the question?
So my question is, in my university lecture, I give every hint on astronomy, but the student submit a report just only say it is very difficult, or the most popular reply is to send a probe. So it's a very pity. So I gave a lecture. So the universe is very huge, and it is difficult to reach even the outside of the solar system. But I disappointed. I cannot transfer the concept to the student.
Okay.
So maybe it's just only show the astronomical concept. It might be or should be beyond the imagination of the current, at least Japanese university students. So it's a very pity. How do you have any idea to break this barrier?
Yes, I think the students will not be interested in learning first about the techniques in astronomy or the calculation in astronomy or that part which doesn't give them a picture. So one thing we should do is when we talk to them, we should try to relate it from the everyday life. We start from the everyday life, talk of some phenomenon, and then relate it to some astronomical object. We can also, for example, in today's conditions, I do not know how good or bad the situation is in Japan as far as this pandemic is concerned, but in people are aware of the situation, and therefore they should consider, for example, the virus, and that can be related to the origin of life. We can talk to them about the conditions on Earth, conditions near other stars, and what makes life possible on Earth, and why we are interested in knowing about exoplanets. If you simply, most of the time in the classroom, we spend most of the time in talking of calculations, showing them the orbits of the planets or the stars, and so on. I think that doesn't interest them so much. Second thing is, in university, perhaps it may not be so much correct, but we can for the younger students, we can do some simple experiments in the class. For example, how the occultation occurs, or whenever there is an astronomical event like there was Venus transit. So at these opportunities should be utilized to tell them about why Venus is in front of that, or why if there is an eclipse, what is a transit, what is an eclipse, why eclipse doesn't happen every month. Orbits of moon and Earth are different. There is an angle. Why the size of the planets that appear in the sky keeps changing, or the color keeps changing, and so on. And I think we have to, the basic thing is that we relate to the observable to what is not actually directly seen. If we relate it to their everyday life, for example, even a phenomenon of sketching, we can talk to them about the evening sky. We can talk to them about the morning sky. We can talk to them about everyday life experience of sounds. Then can talk to them about Doppler shift. And then we tell them how this Doppler shift is used in detecting exoplanets, for example. Or how we know.
So your suggestion is to deduce or to realize the small part, not the whole thing.
Yes.
I see.
And similarly, the expansion of the universe. How do we know how a galaxy is very far and so on?
I try in the coming year. Thank you. And the one question has come from the Vajapayee maybe the pronunciation is different, but the question is why do we assume ET life mostly use radio wave to communicate?
Yes, this is not entirely a correct assumption. This is based on just the fact that we are advanced. We are using electromagnetic signals to communicate. Of course, electromagnetic signals can move to faraway places, but there could be other forms of communication, or we are using radio waves, for example. Electromagnetic signals is fine, but we are limiting ourselves to radio waves, which is not the right assumption. I am sure that if there is some intelligent civilization somewhere else, they may be trying using some different frequencies, which are beyond the radio frequencies. So I agree with Amritanshu Bajpayee that we should not assume that mostly ET would mostly use the radio waves to communicate.
Possibly which way, alternative way to detect the ET, the thinking about itself is very helpful for the thinking for education.
I think
one of the Japanese astronomer tried to detect laser light instead of the radio wave. So that is one possibility.
The simplest thing, as I was mentioning, a binary thing like 0 and 1.
Mm-hmm.
If the laser light goes, this is 1. If the laser light stops, it is 0. 0 and 1, the binary system, if this is sent in some organized manner, in some systematic manner, like beep, 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 beep. This is a very simple 1, 2, 3, 4 counting, which any intelligent civilization should be able to guess. Or there could be a little bit more difficult series like where we will have the number of beeps would be 1, 2, 4, 8, 16, 32, 64, 128, and so on. There could be harmonic series, there could be arithmetic series, there could be, so any civilization, for example, if we receive signals like this from a definite point in the universe, we would be able to infer that this signal is coming from somebody intelligent. I think I should confess that I think people have not been creative and imaginative enough in trying to communicate with extraterrestrial intelligence. Pulsar gave us some hope, but which was a false hope because this was actually an inanimate object. So we have to think of more ways of communicating with them. The second thing is that many of these objects are so far away. The signals that will reach us would have started there maybe thousands of years ago. We do not know.
And the additional question is the same person. It's a very long question. So the even at the slow pace of currently envisioned interstellar travel, the Milky Way galaxy could be completely traversed in a few million years. And since many of the stars, similar to the sun, are billions of years old, Earth should have already visited by extraterrestrial civilization, or at least their probes, if they exist. Are scientists pondering over this fact, over extraterrestrial life in all directions, or can we infer they are more rudimentary than us rather than being intelligent?
Yes, you are right in the sense that it will take about 100,000 years across our Milky Way galaxy if we travel at the velocity of light. Now, given our present technological limitations, it would definitely take billions of years. Now, any human being which travels in these spaceships cannot survive those millions of years, number one. Number two, we could have robots there. We keep on constantly working. So we have to make sure that they have energy, that much of energy for that. Of course, once you go into the outer space, hardly any energy is needed for keeping you moving. This is more or less by inertia. But then there will be places where you will have to have energy to change your direction and so on. Let us imagine that today we start a spaceship from Earth. It is made of a material which is made to last for millions of years. It goes without robots or with artificial intelligence. But to have robots or artificial intelligence of the level which will be able to tackle the problems on the way, I think we are still a bit away from that. I'm sure that within a few decades, this will be done. And second thing is that if there were intelligent civilizations somewhere else, they would have visited us by this time. I do not believe the UFO stories. I don't think they are the aliens coming to us. There is no definitive evidence as yet. But if there were intelligent civilizations elsewhere, even if they are millions of light years away, if they started millions of light years away, by this time they should be visiting us. But at the same time, I also agree that in such vast universe, where we have tens of billions of galaxies, tens of billions of stars in each of them, or maybe so in them, Earth cannot be the only place where their life is. There must be life somewhere else. Statistics suggest that. There is a famous equation given by an astronomer known as Drake's equation, which says that howsoever small, but there is a finite probability that there would be life on some planets other than Earth. But I think we are still not technologically advanced enough to send our space missions to travel for millions of kilometers. But I am sure that this will be done. Things like Voyager are still traveling, perhaps. They are carrying the message from Earth with human figures and all. So I think someday we will meet them.
Okay, he maybe he replied the Fermi's paradox and Drake's equation.
Yes.
So that's the answer. Okay, and so I think so that the greatest debate should be on to the Fermi's paradox nowadays, I think. But in the science history said the final answer always exists beyond our inspiration. So we should make a research or to find some evidence. That should give some answer. As you said in the last part, if we can find that, or if we could not find that, in either case, we become more happy.
And there is one more question which I see here. And it says that maybe civilizations destroy themselves before they reach that point. Yes, that is what Sagan and other people also said, that maybe due to nuclear warfare and biological warfare, some of the civilizations destroyed themselves. But I think if there were many civilizations, not all of them would have destroyed. Sense should have prevailed in some of them. And I think someday, I'm hopeful that someday, we did not find life on Mars, even though we were nurturing a hope that when rover landed on Mars, so somewhere behind some rock, somebody green monster would pop up. Hey, hello, where are you coming from? That did not happen, but I think someday some such thing would happen.
Okay, thank you very much. And thank you, many good questions and comments. So now it's time is up. So we close this session. Before closing, Aviva, do you have any comment?
I would just, yes.
Okay, thank you very much. Yeah.
Okay, I have no comment for the presentation. It was so great. I like it. I learned so much today. And today we close the session for Asia Pacific in here.